Hi, today I'm going to talk about occupational mobility and a data-driven network model that we developed. I'd like to start by asking you to imagine that a high school student asks you for career advice. They say they either want to become a statistical assistant or an electrician. You do your research and you find out that statistical assistants are likely to be automated while electricians are not. With this information, you might be thinking, well, you should become an electrician. That way you won't be displaced by automation. Well, all this work is about why that would be the wrong answer. And it would be the wrong answer because we would be focusing on one single number instead of acknowledging the complexity of the problem. This is more how the problem looks like. Here in this network, nodes are occupations and link the node job transitions. So you see electricians are blue. They're unlikely to be automated. However, they're surrounded by red, meaning that they might be displaced by other workers as these workers are displaced by automation. Instead, statistical assistants are red, so they might be automated, but there are nearby occupations that are blue, so they might find another job easily. Um, we must clarify that in this work, we think of automation as both destroying and creating jobs, and this has been seen throughout history. For example, in the Industrial Revolution, some jobs were destroyed, but others were created. And therefore, we're going to focus on labor reallocation. So how do we model the labor market? Well, our system is composed of a network of occupations, and each network has a number of employed workers, a number of unemployed workers, which means they were previously employed in that occupation or in that node and then were fired or separated or quit, and job vacancies. And this is how the model works. A worker begins a time step employed in occupation I. You ask, is the worker separated? No. And employed? Yes. And unemployed. If a worker begins unemployed, you ask that you submit an application at the previous time step. No. Well, please apply to a vacancy in your occupation or in neighbors. And here's where we consider the network structure. You can only apply to occupations that are neighboring in the network. And then you ask, is the application, if they did submit an application, you ask if this application is successful. No, we'll try again. And if yes, is it in the same occupation? If so, you end employed in that occupation, and otherwise you switch occupation. The vacancy side is simpler. A vacancy is open, then you ask, are there applicants? Yes, choose one at random and close the vacancies. No, end the time step open and try the next time step. So how do these workers get separated and how do job openings happen? Well, we think there's two processes. One is spontaneous. There's always a certain probability a worker might be fired or separated. And likewise, there's always a probability a vacancy might be open or separated. But we also think there's some labor reallocation happening because of automation. So occupations that are red, so they're likely to be automated, are more likely to fire workers. And occupations that are blue, so unlikely to be automated, they open vacancies more often. And then we have the job search and matching. Unemployed workers applied for one job vacancy in adjacent occupations. So again, here we have labor market frictions with the network. And then the hiring process. Vacancies which receive at least one job application will hire a worker. We can translate this model into dynamic equations. You can see the details in the paper. And then we go through the macroeconomic behavior and calibration. To calibrate the model, we use the Beverage curve. This curve is the plot between the vacancy rate and the unemployment rate. It's well known that when there's a crisis, unemployment rate goes up and vacancy rate goes down. And when we're recovering, unemployment rate goes down and vacancy rate goes up. There's also a cyclicality on this curve that's important, and we managed to reproduce it as well. Okay, so now we apply to the problem at hand, the impact of automation on employment. So as I said, we assumed some occupations increase their demand because they are not automatable, and some occupations decrease their demand because they are automatable. This is demand for labor. And then we check unemployment rate and long-term unemployment rate, and we compare the occupational mobility network, which has a structure that we get from data, and from the complete network, assuming anyone can apply to any job. And we see there's a strong difference in the unemployment rate and in the spike. Same for the long-term unemployment. Okay, but that's at the aggregate level. What happens for particular occupations? In this plot, dots are occupations, and we have the change in the unemployment rate. and the probability of automation. So for the complete network, we see a straight relationship. The thing that determines your unemployment, how did your unemployment change, is the probability of computerization. But when we consider the network, so you see the green ones have a lot of dispersion, and this is what we call the network effects. And for example, electricians, they at the beginning, since they're not automatable, they decrease their demand, they decrease their unemployment rate because they're opening more vacancies. But as workers of similar occupations or nearby occupations are being displaced, then they start displacing electricians, and you see the jump. So these are the second order or the network effects that we think are important for modeling automation. And one thing that's really curious is that the network structure plays an important role. So here we tried not only the occupational mobility network and the complete network, but a retraining policy where you add more edges, and reshuffled a random network. And there's a lot of different behaviors between unemployment rate and long-term unemployment rate, both at the level, but also qualitative, you see some differences. And this is something we'd like to look more into. So if you have some ideas, please stay in touch. Final remarks, we must consider the network structure. So that's the main point of the paper. And we, on the further work, we want to understand more about how the occupational mobility network affects the labor market. And we also want to apply it to other shocks. In recent work, we showed that the COVID-19 labor shock affects occupations differently. And we had some estimate about it. So we would also like to apply it to this. With that, I'd just like to say thank you. I think it's month 7 of the pandemic, so I'm sending everyone a remote hug. Hope you're doing well, and feel free to email me any questions and some references. Thank you very much.